Hello, everybody, and welcome to another wonderful day of chemistry. So, today we're going to go ahead and take a step back from statistical entropy and look at how we can use entropy to evaluate thermodynamic processes. So, one of our favorite thermodynamic processes is going to be literally the transfer of energy from a surroundings into a system. Specifically, we're going to be looking at what happens when a system is the change in the entropy of the system when it undergoes heating. So the entropy change can be defined based on the minimum amount of heat needed to drive this process. So what's the minimum amount of energy that it takes to go ahead and induce a change in the system? And so thus, in this terms of state function perspective of entropy, we're looking at the change in entropy of a system being based on the reversible amount of heat. So again, that minimum amount of heat needed to drive the process and the temperature of the system, with the idea that, again, at higher temperatures, we see a lower increase in the system, and at lower temperatures, see a greater increase in entropy of the system. And again, we can go ahead and look at this either in the infinitesimal perspective, or we can go ahead and look at it on the discrete perspective, where we'll go ahead and integrate this from the initial state to the final state. Noting that, as we've often seen before, the amount of heat can be related to the temperature itself. So that can make solving this integral a little tricky, and as always, we'll often constrain this integral to give us a little bit better equational form for that heat. But one of the major reasons we defined the change in entropy based on the reversible heat is, remember that heat itself tends to be a path function. But as soon as we constrain it into the reversible condition, it is now going to be a state function. So that really means that entropy is going to be a state function and will only depend on the initial and the final state. This, which is going to be very useful in that we're going to use both in this lecture and then the next, this idea that if I go ahead and I start at initial state and I do a lot of heat and work transfer, but as long as I return to that same initial state, it means the change in entropy should be zero. With especially this working because it's going to be a reversible process, meaning that we have no excess buildup in energy. So again, because I've got a state function, as long as I get back to where I started, I should have a zero entropy. And again, note this will specifically be for the system. So then we can use this to kind of express our entropy in terms of both the system and the surrounding. So how much will when I heat the system, how much will I increase the entropy of the system, and how much will I decrease the entropy of the surroundings? So what we can do is combine this breaking up of our total entropy into systems and surroundings with the second law of thermodynamics, which again says that the total entropy has to increase. So that means the total entropy has to be greater than or technically equal to zero. Now, for a reversible system, for the system, we're going to define the entropy as the reversible heat and the temperature of the system. Now, the surroundings we're going to define very slightly differently, and this is going to be very important. The surroundings is not going to be based on the reversible heat, but instead the actual heat that the surroundings are provided. So this is still technically going to be a state function, but we're going to see a lot more change in that surrounding entropy. And then again, the temperature of the surroundings. So again, if this note that oftentimes the system and the surrounding may be at different temperatures. We can now go ahead and insert both of these equations into our Clausius inequality and find that there's going to be four key parameters we're going to be looking at when trying to evaluate the favorability of a system. What's the minimum amount of heat needed to drive a change in a system, as well as the temperature of the system, and how much heat is actually being provided, and the temperature of the surroundings. And note that this can be very important, that difference in between what's the minimum amount of heat needed and how much heat is actually being provided. So now let's go ahead and look at this for a reversible process. So if I've got a reversible process, This means that any change is going to be very infinitesimal, specifically because there's no major forcing factor. And for a heating process, this means the temperature of the system and the temperature of the surroundings should be equal. So again, that way we aren't going to automatically see the heat go from surroundings to system. It could also go from system to surroundings, meaning the system is at equilibrium the whole time and any change will be very slow. Now, we can also use the definition that since this is a reversible process, the reversible heat gained by the system will be the same as the actual heat lost by the surroundings, because that is also going to be reversible heat for a reversible process. That is a very important note to take here. Now, what we can do is say, all right, again, if I'm looking at a reversible process, that means that if I'm taking the ratio of the heat, of reversible heat over the temperature, this will be the same as the negative of the heat of the surroundings over the temperature. And this is also by definition both the entropy of the system and the negative of the entropy of the surroundings. So this is very important because at a reversible process, it doesn't matter what the reversible process is, the change in entropy of the system should be equal but opposite of the change in entropy of the surroundings. Now let's go ahead and plug this back into our Clausius inequality. So if we plug this in, well then if I add together the system and the surroundings, well they're just negative of each other. That means the total entropy change should be zero. This is also a very good definition of a reversible change. So if a change is spontaneous, that means that the entropy should be great, total entropy change should be greater than zero. If a change is reversible, meaning that it could go either way, then we're at this ragged edge where the entropy is zero, letting either the forward or the reverse process dominate. So this is a good definition of the entropy, the universal entropy for a reversible system. Because at that point, the energy flow can go from systems to surroundings or surroundings to system, because either way, the entropy change is zero. So next time, we're going to go ahead and use these ideas of how we can look at the entropy of a system to go ahead and evaluate how can I make a perfectly efficient heat engine. So until then, take care.